Welcome everyone and thank you for joining us for part 2 of our CODESYS Virtual Control webinar series. If you haven't seen part 1 yet, I recommend catching up on it, but you should still be able to follow along just fine today. My name is Martin Decker, and in this session I'm going to tackle the question that many of you may have been asking after the first webinar: what about safety? Specifically, how can you implement a safety PLC on standard off-the-shelf hardware, including safe IOs, without needing a dedicated proprietary safety controller? To make sure everyone is on the same page here, there's a brief summary of the last webinar. We started with the basic understanding of what a virtual PLC actually is: a software-defined PLC running inside a container on a standard Linux system. We looked at the wide variety of use cases this enables, from centralization and hardware consolidation in large-scale plants to modularization in complex machines and the refactoring of comprehensive applications. We discussed the extensive benefits and we saw a hands-on demonstration including connecting and operating real IOs and a visualization. And we also covered the licensing model, which is straightforward and application-based. All of that laid the foundation for what we're about to discuss today: bringing safety into the virtual PLC world. Now, here's the challenge we've been hearing from our users, engineers, system integrators. You look at the virtual PLC architecture and everything works beautifully for standard automation. But it's all what we call gray, standard, non-safety rated. In the real world, however, there are numerous applications in which functional safety plays a central role. That's why the immediate reaction from most people is, well, that's great, but I still need a dedicated safety PLC sitting next to the regular one. And until recently, that was absolutely true. In the past, and by that I mean the past that still extends into the present, the prevailing view was that safety PLCs could only be implemented using specialized two-channel hardware. And these types of devices are more expensive, their development and certification are complex and time-consuming. So the question I want to ask here is, do we really still need safety PLCs running on dedicated, specialized, expensive hardware? And guess what? The answer is no. And this is the game changer. What you're looking at is a TÜV Süd certificate issued for CODESYS for the CODESYS Safe Control Core. And this certificate confirms that our safety software component is suitable to be used as a safety PLC according to IEC 61508 up to SIL 3 in conjunction with a suitable non-compliant compute device. Now let me emphasize the last part: a suitable non-compliant compute device. That means standard hardware, not a special safety rated processor, not a proprietary module from a specific vendor, standard off-the-shelf computing hardware. The product itself is called CODESYS Virtual Safe Control SL, and it has been tested and certified according to several standards. What does that mean for us? Let's build up the picture step by step. So here's the architecture you already know from part 1, without any safety PLCs. We have a server, IPC or edge device at the bottom, an optional hypervisor layer, a real-time Linux as your operating system, and then multiple containers, each running a virtual PLC instance alongside a licensed server and potentially other services. So this is the standard non-safety architecture. All of these PLC instances handle your regular automation logic like motion control, process control, communication, visualization. Everything works, but none of it is safety rated. Now, here's what changes. We take one of those containers and instead of just a functional virtual PLC, we create a container instance of a virtual safety rated PLC. This is now running the CODESYS Virtual Safe Control SL. It sits right alongside your standard virtual PLC on the same hardware, on the same Linux system, inside the same container infrastructure. And the key insight here is that you do not need to change anything about your hardware. You do not need a separate box. You just deploy an additional container that runs a safety certified PLC. Let's zoom into that safety container to understand how it actually achieves safety integrity on non-safety hardware. The CODESYS Virtual Safe Control SL implements a dual channel architecture. You can see channel 1 and channel 2, with channel 2 marked with asterisks to indicate it's the coded or diversified channel. And both channels run inside the same container on the same CPU. They execute sequentially on a single core, and the key is that they process the same safety logic using different internal representations, and then the results are compared. If anything goes wrong, CPU error or memory corruption, any kind of transient fault, the two channels will produce different results and the system detects the error. And this is the principle of coded processing with diversified encoding, which I'll explain in more detail here on the next slide. Here's a simplified illustration of how coded processing works. Imagine a safety relevant input coming in, and the operation to perform is a simple addition. 1 + 2 = 3. The native channel first processes this normally and gets the result 3. Sequentially, the coded channel then applies a diversification factor, in this simplified example, multiplying by 10. So it computes 10 + 20, which equals 30. Then the comparison step checks, does 3 equal 30 divided by 10? If yes, the result is verified as safe. If not, an error is flagged. In practice, the encoding is far more sophisticated than a simple multiplication factor. It uses mathematically proven transformations that can detect a wide range of hardware faults affecting the CPU, memory, and data path. The important point is that all of this runs on standard non-safety hardware. The safety integrity comes from the software architecture, not from redundant or special purpose hardware. Now here's the complete architectural picture showing how everything fits together in a real deployment. At the top, we have our setup as we already know it. Below that, connected via our industrial network, you have your field devices, HMIs, sensors, drives, I/O and safety I/O modules. So they're still necessary, the safety modules. We can replace the dedicated safety PLC, but not the safe input and output modules. They still need to be physical hardware components in order to connect other physical hardware like sensors or actuators. And on the right side, on a separate second host, you see the second independent time provider. This is the one additional hardware requirement for the safety architecture right now. You need an independent time source that doesn't rely on the same CPU or system clock as the main host. This is used to verify that the safety cycle times are being maintained correctly and that the safety system hasn't stalled or lost synchronization. And that's it. One extra time source on a separate host. Everything else runs on your existing standard hardware. And in fact, we're already working with leading partners to develop a solution that will allow even a second time source to run on the same host while still maintaining a safety rating. Now, before we start the live demo, let me briefly summarize the concept and some important requirements. On the concept side, we run two parallel PLC instances, both the standard CODESYS Virtual Control SL and the CODESYS Virtual Safe Control SL on the same system. That's necessary because the safety PLC only handles the safety relevant tasks, whereas the functional PLC has to take care of everything else, for example, the fieldbus communication. And these two PLC instances exchange all necessary data with each other via shared memory. The two safety channels execute sequentially on one CPU core. Code processing detects faults, and you need a second independent time provider. On the requirement side, you need the CODESYS development system and a couple of CODESYS add-ons, a container engine, Python, a real-time capable Linux, compatible CPU architecture. Currently we support x86 and x64, and ARM support is scheduled for mid-2026, so this year. And you'll need SSH access to the target system for deployment. Okay, enough with the dry theory now. Let's take a look at it right here using this setup from the previous webinar. Basically a multi-core CPU running Debian Linux with a real-time patch and Docker as container engine. Connected to it is an EtherCAT coupler and some I/O terminals, both gray, functional, and yellow for our safety I/Os. Here on my Windows laptop, I already installed all necessary add-ons using the CODESYS installer. So for the live demonstration, I switch to the CODESYS development system and will first go to the CODESYS Control SL to our deploy tool. Here in the first step, communication, we connect to our host. I already prepared that, so I'm connected to the host via SSH. In the next step, I have to make sure that all the necessary images I need are already available on the host, so we can later then create instances of the containers. In our case, we need all these virtual control, virtual edge, virtual safe control, and safe time provider entities, and all four of them are already installed on the device, as you can see here. So we can also skip this step here, as I already prepared it. The interesting part now here comes in the Operation tab. That's for creating instances of all the entities we need. So in our case, we have a license server already running on the device from the last webinar, and I already created a couple of instances we need. Yeah, specifically, one virtual control instance, so one functional PLC, a safety PLC, a virtual one, an edge gateway in order to connect from our development system to the PLCs, and the second time provider which runs on a second host here in my network. So let's start from the top with the virtual PLC. We have to configure it properly so it works as desired, and for this we have to first enter some dependencies here. As we need the edge gateway in order to connect to the virtual control later, the virtual control depends on the edge gateway. Why? The virtual edge, this container instance, is entered as a dependency here. Next, because the functional PLC and the safety PLC are communicating via shared memory, I have to set this flag shareable here in order to make sure that the PLC, the virtual functional PLC, provides a shared memory for later the safety virtual PLC for communication purposes. So it's important to set the flag shareable here. Next, I add the license server here, so it's not only running in demo mode, my virtual PLC, but completely licensed. And as the whole fieldbus communication is handled by the functional PLC, I enter the Ethernet adapter, which is connected to my host here. So the red cable here goes to this ENP3SO, where we will do EtherCAT and FSoE communication later on. So that's all about the virtual control 1. It's properly configured now. We skip control 2 and 3 as we don't need them for our demo. They're just running alongside here and won't do any harm. Let's now get to the virtual edge gateway. It is already pre-configured correctly, so we don't have to change or explain any settings here. It's all default settings that are automatically filled in when you create an instance. But now let's come to the virtual safety PLC here. Here at dependencies, we have to enter two things. First, the virtual control 01, because this functional PLC is necessary for the safety PLC to work properly. And as I already explained before, the virtual safety PLC also needs this second time provider. So in our case, it's this vSafe time provider that's running on a second host here in the network. That's why I enter it as a dependency here. So next, at IPC here, I can tell my virtual safe PLC that it can access a shared memory provided by another container. And in this case, it's the container in which my instance of the vControl 01 we just configured before runs. So that's also an important configuration to do before we start. Next, we have to configure the ports line here. Specifically, I want to map the container port 60,000 on my container to the host's port 60,000 for UDP communication, because that's the port to which later then my second time provider will send the ticks so the safety PLC can work properly. Apart from that, we don't have to configure anything else. Let's have a look now at the safe time provider here. And at the same safe time provider, the most important configuration to be done is specify where the host actually is running, where the safe time provider shall send the timestamps to. And in this case, I just enter my host's IP address here and also specify the port to which the timestamps shall be sent. So we're done now setting up the instances, configuring the instances. Let's go forward now to the actual project. And just a quick side note here, this webinar is not about how to set up a CODESYS safety project from scratch and complete it so you can certify it in the end. It's just to give you an idea of the most important aspects, or at least of some important aspects of a CODESYS project. So the focus here is the virtual safe control, not the project. Anyhow, to give you an idea of how it works, I created an empty CODESYS project here. Right now, there's only a virtual control for Linux in it, but we want to do safety, right? So I add another device. In our case, here under PLCs, I add a CODESYS safe control for Linux SL. And that is listed here in the Add Device dialog once you install the add-on in the CODESYS installer. So I add this device, and in the device tree then, the safety PLC is created with the corresponding safety logic and the safety app. Then, as we want to do fieldbus communication, in our case EtherCAT with FSoE, I add another device just below my main device, the functional PLC. So first I have to add an EtherCAT master here. Below the EtherCAT master, I add my Ethernet coupler. Below the coupler, I'll skip the functional I/O disk here. I go straight to the safe ones. So that's the EL1904. And now pay attention what happens if it gets added here. Automatically, implicitly, another logical I/O is created here below the safety PLC. I'll do that again. So you can now really pay attention to what I just said. If I add the second I/O terminal here, the safety one, the EL2904, it will be added here below the EtherCAP master, which runs below the functional PLC, and a second one will be implicitly added here below the logical I/O. So I go to add device, and here we are. The second one is added here. I want to explain this a bit because that's a crucial point about the safety solution in CODESYS. You remember we just configured the shareable memory between those two containers before, between the virtual PLC and the virtual safety PLC, so they can communicate with each other. And with these I/Os here we physically have on our board and these logic I/Os below the safety control, we can make sure that the data can be exchanged between our fieldbus devices and the safety application. That means they communicate via shared memory on the same host, and we don't need two separate devices. That's for I/O communication, exchange of information from the safe world to the non-safe world actually, or at least to the functional PLC world. And furthermore, it's also possible to exchange variables you declare in your application here. So you could add below the application here another object that is called logical exchange global variable list. I go to add, gets added here, and I can do a mapping. This drop-down menu is currently empty, but if I create here in this case below the safety PLC another logical device, so let's just take byte out object, another object is created here, and this object can now be mapped in this list, which enables me to get data either from the functional application into the safety part, or, well, depending on the object, the other way around. So that's important to understand how this data exchange between the two worlds works. That's basically the most important thing about our setup here. As I don't want you to watch me implementing the whole logic here, I already prepared a second project here. Maybe before we do that, let me go to the deploy tool again. We're still connected here to our host, and I want to log in now. Before we can log in to this whole setup, I have to start the instances of my containers. And I'll only start that one, the safe control 01, and it has some dependencies, the vcontrol1 and the safe time provider, and the vcontrol1 has another dependency, the vEdge. We will build a chain of instances that will start one after another. So if I go to start selected, I get a message saying there are some dependencies and all instances will be started subsequently. So I go to yes, and now it will take a little time. As you can see here in the message window, we're first starting the virtual safe time provider, then next the virtual edge gateway is started, now the virtual control 1 is started, and the virtual safe control. Once all these instances are running, we should already see, or should soon see, some lights turning on here because the application already started running. So meanwhile, I'll switch to this ready-made project which already contains all the logic and all the proper configurations for the connection to the I/Os. Let's now connect first to the functional PLC. For this purpose, I have to select the virtual edge gateway, which is in the same container network as the PLCs here, the virtual ones. I scan the network, connect to the PLC, and then, well, I selected the wrong application up here. It's still the safety application, so I, of course, want to log into the functional one. Enter the login credentials for the runtime. And here we are. You see everything is green and running. I can also log in here to the safety application. So select that application here. Do the network scan again using my virtual edge gateway. Connecting to the safety PLC now, and I can also log into the safety PLC now in order to check if everything is running properly there. Get asked a safety related question, confirm that one, and I'm logged in to the application here. Let's have a look at the POU now. So we're online here. We're seeing values coming in, going out. Everything works in a safe mode. Perfect. With the whole setup running smoothly, that's it for the demo now. I switch back to my presentation. And now that you've seen the virtual safe control in action, let me give you an overview of where things stand today and what's coming next. For functional applications, we support the major industrial field buses. For example, EtherCAT, Profinet, Ethernet IP, and all the other field buses and communication protocols that are supported by our regular PLCs or soft PLCs. And for safety applications, we currently support Profisafe host in versions 2.4 and 2.6, as well as FSoE master, that's failsafe over EtherCAT. So you have a choice of safe fieldbus protocols to connect your safety I/O devices. In terms of architecture, functional applications can run on both x86 and ARM processors, on IPC servers, on edge devices. And safety applications currently only run on x86 CPUs. As I mentioned, ARM support for the virtual safe control SL is planned for mid-2026. Looking ahead, we're also working on orchestration support via Kubernetes, Docker Compose, and OpenShift, which will make it even easier to manage and scale your virtual PLC deployments in larger installations. As you saw in the first webinar, virtual PLCs offer a wide range of benefits. Some of them are listed here on the left-hand side. I won't read them to you now. But when combined with virtual safe control, they offer even more. Well, let me walk you through these benefits, although I think they really speak for themselves. You're working in one comprehensive ecosystem. That means everything from the functional logic to safety parts, as well as visualization, fieldbus, the whole engineering is accessible in one CODESYS project and via one engineering environment. The whole solution is safety certified to meet IEC 61508 SIL 3, and you can choose from major safe field buses, Profisafe and FSoE, so you're not locked in into a single vendor's I/O ecosystem. And time to market. As there's no safety hardware development and its certification involved, and the virtual safe control already certified, you can reduce the certification process for your entire system by up to several years. So we believe that we've built really something that stands out in the market, and I'd encourage you to compare for yourself. And here's what sets CODESYS Virtual Safe Control SL apart. The TÜV certification we hold is independent of specific hardware, and that's the key difference. The certificate applies to our software component, not to a particular processor platform. And the only hardware dependency is the second time source, and that's deliberately minimal. When you compare this to what else is out there, be aware of a few pitfalls. You may see announcements about virtual safety PLCs from other vendors that are still under development, not yet certified, not yet available. You may see coded processing solutions that, while technically similar, remain bound to specific hardware platforms and therefore don't give you true hardware independence. And of course, there are conventional safety PLCs with dedicated hardware, which work but come with all the cost, complexity, and procurement challenges we've just been discussing. So when someone tells you they also have a software-defined safety controller, ask the question, is it certified? Is the certification hardware independent, and is it available today? If you like to try this yourself, here are resources to get started. You can get the CODESYS Virtual Safe Control directly from the CODESYS store or through the CODESYS installer. The link is on screen and in the video description. For documentation, the CODESYS online help includes 2 particularly useful guides. The Safe House scenario, which walks you through a complete safety application example, and performance optimization, which helps you tune your deployment for best results. And on the CODESYS YouTube channel, you'll find video tutorials that walk you through the setup and configuration process step by step. Finally, let's briefly discuss licensing, since that's something we're constantly asked about. The safety licenses follow the same application-based model we use for the standard virtual control. The tiers are based on the number of safe connections. That is, the number of safe I/O devices you connect to the safety controller. So the exchange variables we've just seen in the project with the standard controller do not count as safe connections. The range here starts at safe control 4, which gives you 4 connections, and scales up to a possible 192 connections. These are per instance one-time license costs. When you compare that to the price of a dedicated safety PLC, typically several thousand euros for the hardware alone plus engineering and certification effort, the actual value of our solution becomes very clear. Before we wrap up, let me point you to the rest of our webinar series this week. Tomorrow we have 2 sessions on CODESYS 4, our new web-based IDE, and the day after we have 2 sessions on engineering and AI. All sessions are offered at 2 time slots, early morning and afternoon Central European Summer Time, so hopefully one of them fits your schedule. Now, thank you for joining today's session. If you'd like to learn more, visit our website, or you can also find us on YouTube, LinkedIn, and Instagram. If you have any questions, feel free to reach out. You'll find contact information in the video description as well. So, thank you for your time today and enjoy working safely with CODESYS.